This is the second lecture in Chapter 13 about kinetics or rates of reaction. And this lecture will focus on what is called the differential rate law. As you'll find out, there are two rate laws, differential rate law and integrated rate laws. The differential rate law is probably the more commonly used one. I'm going to give you the basics about the differential rate law. At some point, you'll probably want to make a side-by-side comparison of the two rate laws. The differential rate law, which from now on we'll just call rate law, describes the relationship between the rate of a reaction and the concentrations of the reactants. Okay, between the rate and the concentrations of reactants. The rate law must be determined experimentally. It's not anything you can determine from looking at the balanced equation. The premise for the differential rate law is that rate is directly proportional to the concentration of each reactant raised to a power. So reread this statement while you look at this math expression, okay? The rate of a reaction is directly proportional to the concentration of each reactant raised to some power. Now, this power is what requires that you do an experiment. You can't determine the power that the concentrations are raised to unless you do several experiments. The exponent is called the order of the reaction for a particular reactant. So another possible rate law for this generic reaction might be rate equals K is a rate constant, which we'll talk about. Reactant A raised to some power, determined experimentally. And it may also be dependent on the other reactant, which is B raised to some other power, also determined experimentally. So this can get a little complicated, so it's important that you're alert and listening. So here's our generic rate law. Remember that the exponents are called the orders of the reaction with respect to each of the reactants. If you're ever asked about the overall order of a reaction, you add the exponents together. Add all of the exponents together to get the overall order of the reaction. The order of reaction is almost always 0, 1, or 2. K is the rate constant. Its units are important. We will go over that later in this lecture, and the units are different depending on the order of reaction. The order of reaction is particularly important because it tells you how much that particular reactant contributes to the overall rate. Obviously, the higher the exponent, the more important of a contribution the reactant has on the rate. The rate constant is something that you will learn how to calculate using the rate law. So I've mentioned that we can only determine rate laws through experiments, so we're going to talk about how we do that now. I mentioned in the Introduction to Kinetics video that the rate of a reaction changes over time. It decreases over time. And I also mentioned that since the reaction changes over time, we can measure it at several different places by placing a line tangent to the, well, that's supposed to be a straight line, tangent to the curve at various places. So to be consistent and also to simplify things, when you're doing experiments to determine the rate law, we use what's called the initial rate method. That's important to understand, okay? So that means we measure the rate of a reaction at the very beginning, okay? That's the initial rate right there, initial rate at the very beginning of the reaction. That simplifies things because at the beginning, all you have present are reactants. The reverse reaction is not really a significant consideration in the beginning because you haven't built up enough products for the reverse reaction to be significant. So initial rate methods are used to determine differential rate laws, okay? The initial rate method is used to determine initial rate laws. This is really just a recap of what I already said, but there's some important points. Generic expression for the rate law. Just maybe restating the obvious, but the rate law only includes concentrations of reactants. Concentrations of products do not appear in the rate law. The rate constant is the little k, must be determined by experiment. And the exponents in a balanced chemical reaction have nothing to do with the exponent in the rate law. So don't be trying to plug those in. Right, so if there is a reaction that has more than one reactant, which is very common, you have to experimentally determine the order of the reaction with respect to each reactant. And so that can end up being a lot of trials or a lot of experiments to do that. Remember that we're going to have to determine the initial rate of a reaction. So basically what chemists do is they vary the concentration of one of the reactants while holding the concentration of the other constant. And they determine how this one reactant affects the rate. And then they hold that reactant constant while they change the other reactant and again determine how it affects the rate. You actually have a lab you're going to do on this method of initial rates. I want to point out just a couple of basic things from these graphs. They're not going to make a lot of sense to you yet until the end of this lecture. The first thing I want to point out is let's look at a zero order reaction. Let's look at the line we get when we plot the concentration of the reactant over a period of time. The first thing I want you to notice is that it's linear and not a curve. That's unusual, okay? What that means is that the rate of the reaction is constant. It's not changing. So just like all of the other, so if it's zero order, the rate is constant. I guess that's the important thing I want out of it. Why would that be? Let's look at a zero order rate law, okay? If n is 0, meaning that the reaction is zero order with respect to A, what does that mean? That means that anything raised to the 0 power is 1, so that means the rate is only equal to the rate constant K. The rate doesn't depend on the concentration at all, okay? So that's the first thing I want to point out. Along those same lines, a reaction that is second order is going to undergo a much more rapid change in rate than a reaction that is first order. So if you were to go along and draw a bunch of tangents to the second order curve, I stink in drawing tangents, you would notice the slope of those tangents are changing much more rapidly than tangents that you might draw along the first order reaction. So for a second order, the rate itself changes much more rapidly. And that's because it is it's more highly dependent on the concentration of the reactant than is a first order. This is another way, the graph on the right is another way of looking at things. So pay attention to the graphs because this can trap a lot of students thinking they might be the same. Notice that the graph on the left is concentration versus time. And so that's a classic kind of rate of reaction graph, changing concentration versus time. The graph on the right, they've already calculated the rate, or they're following the rate of reaction, okay? So the graph on the left, we have to get the rate from the tangent. The graph on the right, we already have the rate along the y-axis, and concentration on the x-axis. So just as I said before, a zero order reaction has a constant rate. and it doesn't depend on the concentration of the reactant, right? And let's look at a first order reaction. A first order reaction is the concentration of the reactant is directly proportional. There's a 1-to-1 relationship between rate and concentration, and that's why you see this perfectly straight line, okay? A second order reaction, the rate of the reaction is exponentially dependent on the concentration, and there you see an upward curving line. So keep those in mind. That's probably a graph that you want to come back to and look at when you understand rates a bit better. All right, so now we're going to talk about actually going into the lab and conducting an experimental method to determine the differential rate law, and that's called the initial rate method. And basically, you run a chemical reaction over and over and over. If you have two reactants, as I said before, you hold the concentration of one of the reactants constant while you change the concentration of the other, and that allows you to find the effect of each reactant on the overall rate of reaction. So here's an example. Here's the reaction between the ammonium ion and nitrite ion to make ammonia or nitrogen gas. And this is the method of initial rates. And again, you have a lab that's similar to this. So look, there were 6 different experiments done. And you can see, compare experiment 1 and 2, for example. You can see they held the concentration of the nitrite ion constant in these two, while they varied the concentration of the ammonium ion. Okay? And then in turn, let's compare experiments 4 and 5. Here they held the concentration of the ammonium ion constant while they changed the concentration of the nitrite ion. And then, of course, they measured the rate of reaction for all of these. So now that you kind of have a handle on what you're looking for, let's kind of take a glance and see the information that we can get from this. Let's go back to comparing experiments 1 and 2. We're trying to look for the effect of ammonium on the rate in experiments 1 and 2. If we double the concentration of the ammonium ion, what happens to the rate? The rate doubles also. What does that mean? That means there is a 1-to-1 correlation between the ammonium concentration and the rate of reaction. Whenever you see a 1-to-1 relationship, that means first order. So if I were to start writing a rate law for this, I could start, and I'm running out of room. Okay, rate equals, you always have to write that little k, lowercase k for rate constant, times concentration of the ammonium, and we just determined that since there's a 1-to-1 relationship, it's first order. Now we have to look at the table again and try to figure out what the order of the reaction is with respect to the other reactant, the nitrite ion. So let's look at that now. If we compare experiments, actually we could compare experiments 4 and 5 or 5 and 6. So looking at experiments 5 and 6, where we hold the concentration of ammonium constant, here you can see if we double the concentration of the nitrite ion, what happens to the rate? It roughly doubles. You're not going to have perfect. It's like 2.1 or something. You're not going to have perfect data because it is a lab experiment. And so the order of the reaction with respect to the nitrite ion is also first order because there's a 1-to-1 relationship, directly proportional to the rate. And so let's look at the overall rate. It's directly proportional to each of the reactants. Okay, so the rate law is simply this. And it's understood that the exponents for both reactants are 1. So you can just leave them out if they're 1. And that's it. That's the differential rate law for this reaction. Remember that I said if you're asked about the overall order of a reaction that you add exponents together. 1 plus 1 is 2. So the overall order of this reaction is 2. So here's another example that I want you to try on your own. This is probably the first, it's not really math, but the first type of problem that we've run into in kinetics that you need to be able to solve. So give this a try on your own. Again, here's the generic form of the rate law. You need to investigate the effect of the concentration of every reactant on the rate. There are 3 reactants. You have to investigate them separately to find their exponents or the orders. And so on the next page, there's going to be a table of data, and I want you to see if you can find these orders of reaction. So here's the table. So what I recommend now is putting the video on pause and seeing if you can figure it out yourself, and then I will go over it. So I hope you were able to at least do some of it on your own. And here we go. Let's look at the bromate ion first. That's called bromate. It's kind of a funky ion. And so if we're investigating it, we want the concentration of the other 2 reactants to be held constant. So the first thing to do is determine which experiments you're going to look at that will hold the other reactants constant. And that would be experiments 1 and 2. Okay? Bromide and hydrogen ion are held constant. So as we double the concentration of the bromate ion, what happens to the rate? It also doubles. Okay, 8 times 2 is 16. Notice the exponents. Use your calculator if you need to. And so there's a 1-to-1 correlation. So the order with respect to the bromate ion is 1. Let's look at bromide ion now. What are the 2 experiments we need to compare where the other concentrations are held constant? That would be experiments 2 and 3. Okay, see these are constant, those are constant. We're just looking at this. So if we double the concentration of the bromide ion, what happens to the rate? It also doubles, okay? 1.6 times 2 is 3.2. So it's also first order with respect to the bromide ion. All right, so now let's check out the order with respect to the hydrogen ion. What are the 2 experiments we compare? So I think that looks like it would be experiments 1 and 4. So the first one up here and the last one. As you see, the concentration of the hydrogen ion compared between 1 and 4 is changed by a factor of 2. The others are held constant. Bromide ion is constant between 1 and 4, and so is bromate. And so what has happened to the rate of experiments 1 and 4? Well, this one's a little odd. Let's see. I always like to do the larger number over the smaller number so that I get a number that's greater than 1 instead of a small fraction. So I'm going to put that in my calculator. Let's see, the rate of experiment 4, 3.2 times 10 to the minus 3. The rate of experiment 1. Okay, so if you put that in your calculator, or perhaps you can see 8 times 4 is 32. That is going to be 4 times faster. Okay, so what has happened? What's happened is when we double the concentration of the hydrogen ion, the rate quadruples. There's not a 1-to-1 relationship anymore. This is characteristic of a second order reaction. So it's second order with respect to hydrogen ion only. So let's put all of these together. The final rate law, differential rate law, of course, always the rate constant. We've determined that the order with respect to bromate is 1, the order with respect to bromide is 1, and the order with respect to the hydrogen ion is 2. The overall order of reaction is 4. Oh, it's right there. Okay? So here's a summary of the relationships. If you have a first order reaction, that means that there is a 1-to-1 relationship between concentration and rate. It means if you double the concentration, the rate doubles. If you have a second order reaction, when you double the concentration of that reactant, you will quadruple the rate of the reaction. And if you have a zero order rate law, that means that there is no effect of the concentration of that reactant on rate. So that means if you double concentration of a zero order, it will have no effect on the rate whatsoever. I want to present the math approach to solving this, and I'm pretty sure that's what your lab is going to ask for also. But basically that involves a rate. So let's compare trials or experiments 1 and 2 first, and you can see by looking at those that the concentration in the nitrogen monoxide is held constant. The concentration of hydrogen gas is doubled, and the rate of the reaction upon doubling the concentration of hydrogen gas also doubles. So intuitively, you can see there's a 1-to-1 relationship, and that says that it's first order with respect to hydrogen gas. But I want to show you a mathematical way of demonstrating that you understand that. If I write a generic rate law, so the rate of the reaction equals a rate constant times concentration, we're talking about H2 at this point. We'll say the order is X, so pretend like we don't know it. Now, if we double the concentration of hydrogen ion, it's like we did going from 1 to 2, what happens to the rate? The rate also doubles. So what mathematically does X, or the order of reaction, have to be so that this is mathematically true? When we multiply the concentration by 2, the rate changes by 2. The only way that can mathematically be true is if the order of the reaction is 1, if the exponent is 1. So that's one mathematical way of demonstrating the order. That's kind of, ignore my dog please, that's kind of a shortcut math way, but there is a math way which your textbook shows and which I feel compelled to show you briefly. You won't be required to do that on my test or if you're in my lab, but I know there are some lab instructors that like you to do it this kind of slowpokey way. So I'm going to show that to you on the next page. All right, so what that kind of slowpokey way is the ratio of the rate of experiment 2 versus the rate of experiment 1, or it could be whatever 2 experiments you're comparing. I always like, as I said, to put the larger value on top because I don't like working with fractions. And then you're going to put what is the rate of experiment 2 equal to generically? The rate constant times the concentration of the reactant you're concerned about, raised to some power, which we're going to pretend we don't know yet, and the rate of experiment 1 is same general expression. K's are going to be identical, the X values are going to be identical. The only thing that has changed is the concentration of H. So we'll put a little 2 here. That's the concentration of hydrogen gas in experiment 2. This is the concentration of hydrogen gas in experiment 1. Let's plug in the values. So the rate for experiment 2, 1.4 times 10 to the minus 4. The rate of experiment 1, 7.01 times 10 to the minus 5. The K values are the same, so they're going to cancel. It's all the same reaction, so it has the same reactant, the same rate constant, So the concentration of hydrogen gas for experiment 2 is 0.280. The concentration for hydrogen gas in experiment 1 is 0.140. And now if we simplify this, 1.4 times 10 to the minus 4 divided by 7 times 10 to the minus 5 is 2. K's cancel out, rate constants cancel out, and since x is the same, we can say now that 0.280 divided by 0.140 raised to the x power. Okay? Simplifying that, we get 2 equals 2 raised to the x power. Implies that x has to be 1. All right? So that's how you prove mathematically. And so I'm going to start writing out the rate. We just determined that the order with respect to hydrogen gas is 1. What is the order with respect to nitrogen monoxide? You can go through the math or do it intuitively, but I prefer to do it intuitively. And so if we're trying to find the order with respect to nitrogen monoxide, we want it to change while the other one stays constant. So that is comparing experiment 1 or trials 1 and 3. And so what have we done between 1 and 3? Well, 0.0114 divided by 0.00570 is, that's just very close to 2. So we have increased the concentration of nitrogen monoxide by a factor of 2 from trials 1 to 3. What has happened to the rate between trials 1 and 3? You can put that in your calculator if you want. Here's the ratio. But I can tell just by looking, 7 times 4 is 28. I can tell that's going to be quadrupled. Okay, so there's a when there's a quadrupling effect, the order with respect to that reactant is second order. And so here is our generic rate law. Now, in order to be completely correct, you need to find rate constant. And I'm going to show you how to do that. It's very, very important to be able to do that. So you're going to want to wait and listen to how to do this when you're alert and paying attention, because it's one of the more difficult things to do. When trying to find the rate constant, K, you want to go back to the original table of data and plug in the values for any one of the trials. There's a rate and there are concentrations that you'll plug in, and that therefore you will then solve for the rate constant. So I just took the values from experiment 1. Here's the rate from experiment 1, and here are the concentrations. Don't forget to use the orders with respect to each of the reactants. And I'm also going to include units. They're just as important as the numbers because you will always be asked to express the rate constant with the correct number of units. And the units will vary depending on the overall order of reaction. So here goes. Let's see. The units for rate is always concentration over time. So, and that's typically molarity. And in this case, time is seconds. The units for concentration is just molarity. Okay, and that since it's an order of 1, it's just simple molarity. And units for this, since it's an order of 2 or squared, is molarity squared. All right, so pay attention to those units when we rearrange to solve for K. So now it's just a matter of algebra. Let's go ahead and do the math and see what we have. I'm going to try to do it stepwise for you. Okay, so I'm going to go ahead and square 0.00570 and then multiply it by 0.140. And I get 0.0000455, okay, or in scientific notation, 4.55 times 10 to the, what is that, 1, 2, 3, 4, 5, 6, 10 to the minus 6. All right, so now rearranging that means that our rate constant K equals 7.01 times 10 to the minus 5 divided by 4.55 times 10 to the minus 6. And that equals, we have about 3 sig figs, 15.4, okay? Now you need units, okay? So on the next page, you just carry your units, do the same thing to your units that you did to the numbers in the calculation, and you'll be good. I'll show that on the next page because I'm too short on space here. All right, so here's what we have so far. Let me go ahead and simplify this just as I did the equation when it had numbers. This is the units for rate. I'm just going to simplify. This is molarity cubed now. And so K, the rate constant, equals molarity per second, and now you got to divide both sides by m cubed. Okay, so now you need to simplify. So the units for K in this case are 1 over seconds times molarity squared. Now, just so that you are familiar with another way of expressing that, remember what molarity is. Molarity is moles per liter, so sometimes you will see that expressed as, let's see, so it would be liters squared seconds times moles squared. So see, here's the molarity squared. So sometimes you'll see it like that. All right, so this reaction overall was third order. Okay, 1 plus 2 is 3. And so I will tell you that the units for third order will always be the same for the rate constant. That's 1 over seconds times molarity squared. And you will see a pattern in the units as you work it out for second and first order. But that I did a hard one here just so you can know how to do the others. And this summary slide is the last slide. I really probably should have put this in after the first lecture and not this one. But if it's useful to you, great. If not, that's the end of differential rate laws. And the next third lecture out of chapter 13 is integrated rate laws.